from Dan Daly from Intel. It's about Linux networking and the OVS as a pipeline. So let's take it away.
Hello, my name is Dan Daly. Today I'll be talking about the Linux networking stack and OVS as a pipeline. So this is a project that we've been working on over at Intel with feedback from the broader community in terms of trying to take our original idea, which was to add P4 to OVS, and instead look at how we can move the entire Linux networking stack into a pipeline and then describe it in a programmable language like P4. And so to go back to the fundamentals of what we're doing, inside of OVS, we are all very familiar with how flows are handled, and OpenFlow is the basis of OVS today. And we started with the exact matches, and then we moved to mega flows. And this serves us very well. It's a very general purpose engine for putting these flows into the data plane. You have some issues though. Most of them stem around when you start to build these different types of combinations, you get these combinatorial explosions where when two seemingly simple functions, when they're combined together, blow up the table size, maybe they blow up the table complexity and makes it hard to scale. You also have these issues where maybe just one small change in one of the tables can cause all of the other tables to have to change because you have built out this sort of interdependent mega flow system where nothing can overlap. That's very different to how a pipeline works. So the pipeline has its roots in sort of fixed function hardware or ASICs that's in a switch or in a router that has a very clear set of functions. We evolved that over time to be able to say, well, let's have that be a programmable pipeline. And these pipelines are much better at handling sometimes independent functions running with their own set of tables where you can build that out into a sequence so that you don't have those those explosions when you do the combinations. The drawbacks of a pipeline is that you need to have knowledge up front of what your pipeline needs to look like so that you know what is going to be programmed by the control plane. And these pipelines really love wildcards. They like to use TCAMs and longest prefix match types of functions that are straightforward in hardware, but sometimes more difficult in software. And so we think that these two issues have been recently resolved. I think we have better approaches to doing wildcards in software. And in the case of trying to put the Linux networking pipeline into the Linux networking data plane into a pipeline, we know upfront what functions we want to put in there. And so that led us to go down this direction where we want to use this P4 control plane that is here on IPDK, get more information about how it works. And all of the code is open source and there for you to see. And we've taken our original P4 OVS concept and moved it into a much broader scope of looking at Linux in terms of not just OVS, but routing, IPsec, and acknowledging that some of the functions in OVS come through the Linux kernel. And so we wanted to bring that all together as one piece. And so where we're starting is that we want to use the Linux kernel, the existing Linux behavior as our golden model. This is if we have a question as to how should Linux as having its own pipeline, how it should behave, it's very simple. It should behave the same way it did before we added this pipeline model. And there could be in different implementations differences between the two. Those just need to be called out, or preferably just not allowed because it makes it more complex to have to describe the eventual behavior of the implementation. So the goal here is to have the Linux kernel be the golden model And you may get other benefits of having this pipeline in terms of performance, in terms of separation, but the behavior must be the same. So I'm going to go into an example of how we build out this pipeline. But one concept that I need to go through is this concept of a port representer. So on the host side, we're going to have some number of net devs, just like we do currently. And these net devs get connected into VMs, containers. Maybe there's an app just running on the bare metal host that needs to attach to the network. These net devs work like the kernel does before. These net devs can also be passed into a VM, and they work exactly the same way. And then inside this port representer space, we're going to have, for each of the host net devs on the left, we're going to have a port representer that we use to say, if some traffic needs to be trapped to this Linux control plane because the coprocessor can't handle it, the fast path can't fully process that packet, we're going to trap those packets into these port representers. And so those are represented in blue. And then on the network side, we're going to have another whole host of port representers that are going to also have a similar relationship to what's on the host, but they're going to be network facing. So there is a net dev on the host where all the traffic that isn't going to a VF or a VLAN or a bond that came in on port 0, came in on the physical uplink 0, there's going to be a net dev for the packets that are trapped on the network side and trapped into the Linux control plane. So if you can think of, if we're putting sort of a bump in the wire in between the net devs on the host and the network, we sort of have to, there's a doubling that happens where we want to move the networking that's on the host. We want to move it either to a different place on the host or maybe onto a different system altogether. And that causes this doubling where we have to have two sets of representers. And that will also be reflected in our OVS bridge configuration. So here I've tried to color code each of the different interfaces. And when you go to start to set this up in OVS, it'll look very similar, except we're not going to use the net devs from the host like we normally do on OVS when OVS is sort of monolithically integrated with the host control plane. Instead, we're going to take these representers and build bridges out of them. So I'm going to take a simple example where what I want to do is I have created some number of 2-port bridges. This is not a restriction. You could have a bridge with any number of VXLAN tunnels and host ports and VF ports and whatnot. You can mix this up as much as you want. But in this simple example, if a packet came in on VXLAN 1000, it will be bridged in bridge 100, and then it will be sent to the VLAN 100 on the host. And so to set this up in the Linux control plane, I take the blue port representers and the yellow network port representers, put them in a bridge, and this gives me that mapping, that connectivity. So when a packet is known and comes in on VXLAN 1000, I know the DMAC, I know where it's supposed to go, and I know that the SMAC has already been learned. I just forward it directly, not shown in this picture, to the gray net dev shown in the previous slide. Now, if a packet comes in on VXLAN 1000 and is unknown, or the SMAC hasn't been learned yet on bridge 100, then I will trap it to the Linux control plane, and then I will have Linux process that packet. I'll have OVS process that packet exactly how it would have before. And I'll show in a little bit of how we made a patch to OVS such that as those unknown packets pass through, if we learn a new association of a MAC to a port, when that port can be a physical port or a tunnel or a port with a VLAN, things like that, then that association will be pushed into the data plane using P4. So you can see in this example, what you end up getting is you'll start learning MAC addresses across these bridges. You'll start populating ARP and ND tables to be able to associate, for example, the IP address of that VXLAN tunnel with the MAC address that's been learned. So you'll start to build out the overlay networking in the Linux control plane, and then start to populate through OVS MAC addresses in each one of these bridges. And the OVS configuration kind of looks like this. And it's sort of busy. But what you can see is that the same, what I just showed in the earlier picture is now here as OVS configuration. And here I am using only port representers in this case to be able to wire up the Linux control plane so that when a packet isn't fully forwarded by the P4 pipeline, it gets popped up into OVS just like it used to before on physical NetDevs, but now I'm using these port representers instead, again, to get that folding effect where I've popped up I've separated out the control plane from the data plane. And you can do the same configuration not just for VXLAN and VLANs, but you can do it for physical ports, VFs. You can put VLANs on a VF. You can really mix it up. And you can use the same configuration to do sort of a infrastructure as a service SDN controller. So OBN could also be building out within their virtual layer 2 domains the set of VXLAN tunnels that go to each other vSwitch on that same domain, and it can have multiple VFs, multiple VLANs attached to that bridge, depending on your configuration. So the goal of this is for a SDN controller to find this very, very familiar in that, yes, we are using port representers, but from the perspective of the SDN controller, they still have their virtual bridges. They're going to populate those virtual bridges with VFs and VLANs and VXLANs in exactly the same way they did before. And the fact that we are having this new data plane in P4 is an implementation detail. Maybe it goes faster for that SDN controller, but we have we've separated out the control plane now from what's running on the host. And now that gives us an opportunity to go and optimize the data plane on underneath that P4, and that could be either in software or in hardware. And so more details on how this flow works is in that P4 control plane link I shared earlier. But what will happen is when I have that previous configuration, I am going to convert the Linux configurations and the OVS configurations into operations either through SCI, which is the switch abstraction interface, or through P4 directly. And this is so that we can take the configurations from the kernel, take the configurations from the OVS, and put them into the pipeline so that the pipeline continues to behave exactly like the Linux does. And so to walk you through the first item, we will, in our Linux control plane, create a bond, create a lag. And that will happen in the Linux control plane itself, not in the host, but in the Linux control plane, it will say, create this bond. And Infra P4D has this feature called the kernel monitor, which will see that over netlink that this configuration has happened. We'll configure the lag creation over SI. And in the case of IPDK, we are translating that SI into something called the table-driven interface, which will then get applied to the target. And that target could be software, could be hardware, anything that is compatible with that API, with that set of tables. Similarly, when OVS goes and creates a table, a tunnel, it will that will get passed through to Linux, who will then create the tunnel, VXLAN, Genev, whatever. And the kernel mon, again, will listen to the netlink socket, see that that tunnel was created, call the same SI function, and then that gets converted to TDI, and then that also gets put into the target. An extra step is needed in VXLAN because when you create that tunnel, all you have is the remote IP address. Keeps it very simple. So Linux has to have that map that says, all right, well, this remote IP address maps to this MAC address in the ARP table that is also copied from the Linux into the data plane, such that when the MAC address is learned, you know when you're encapsulating that VXLAN, you know what MAC address to put it on, and then the data plane knows which port that MAC address is associated with. And so having the Linux as the control plane provides us all of that nice mapping that's already there, lets us leverage that without having to make lots of new changes that may perturb the behavior. And then when the pipeline finds a packet where it either doesn't know the destination MAC within that bridge context, or it doesn't know the source MAC within that bridge context, it will trap the packet up to the port representer corresponding to where it came from. So it says, hey, I don't know what to do with this packet. It came in on VF number 5. So the packet comes up in port representer for VF number 5, goes through the whole Linux control plane. It gets all the way up to OVS, and then OVS says, oh, well, this is a new MAC address that came in on VF port 5. And so the patch that we've made to OVS is for it to, instead of creating a new rule and putting this into its data plane, which it will continue to do, it also goes and sends a P4 runtime call that very simply says, this MAC address should be associated with this port. And again, the port could be lots of different things. This logical port, whether it's a tunnel or a port and a VLAN, all the different types of tunnels you have, ports you have in OVS, we then put that into the pipeline. So our virtual layer 2 tunnel gets populated by OVS. And so the event rate of that is much, much smaller than the event rate that you have today with flows, because the flow event rate happens at every new TCP connection, every new flow in both directions that hits the pipeline. Well, this is going to be at a layer 2 level. Every time a new MAC address is found by OVS, we add it in there, and now it's in the hardware data plane. And not shown here is that to preserve the kernel behavior, we not only need to learn the MAC address, but we have to put the connection tracking for some of the other features not shown into the hardware itself. That's for another day, but we're just talking today about layer 2 and how we expand on that further. And so here is the pipeline. If you look at the P4, this is what you would see, is that there's an ingress classify matches on all the different types of sort of logical ports and classifies it. It says, this is the logical port here that the packet came in on. That's also the logical port that the packet will be trapped on if it doesn't match in the virtual layer 2 table. And so the virtual layer 2 table will look up by the bridge ID, the DMAC, and whether or not the SMAC is learned. If all these things match, then it will forward it to it will associate it with this egress logical port and then modify the packet according to that logical port. Now, an important piece of our pipeline is that if it's an encapsulation it will actually pass through the pipeline twice, which allows us to then potentially route the packet based on its IP address or hash across it multiple ports for lag. And so this virtual layer 2 pipeline has to understand that as well to be able to support different link redundancy strategies. And so why this is really powerful is that it makes these types of combinations where you have independent control planes running at the same time, each have their own little piece of heaven in the P4 program where they can put their rules in with their match and action conditions. And that can be separate from some other control plane also running in the Linux control plane. But maybe in the case of OVS, we're looking at virtual layer 2. And in the case of FRR and strongSwan, we're looking at virtual layer 3. And so with this Linux as a pipeline, we are aiming for full feature fidelity. And the whole reason why we want to do these types of features is because we want to enable the capability of optimizing the data plane and also starting to offload more of these functions into a device such as an IPU. And this is a refinement of our original look at this, where we started with a P4 OVS, and now we've come to a much simpler set of patches for OVS that is just triggering the functionality where I want to go and enact on the data plane. I do that at a very high level of abstraction, for example, associating a MAC address to a port. And when you have the entire Linux as a pipeline, it supports a really interesting set of combinations that people would use in a real deployment. For example, if you're able to run OVS on top of a routing context where you can do ECMP to multiple uplinks, that can really help you in terms of being able to be resilient to links going down or routers going crazy, things like that. In addition, you could think about, well, what if I want to offload for my tenants, I want to offload their IPsec. And in that case, I can start to program IPsec rules using strongSwan. And then I can put that into the context of each individual tenant at layer 2 using OVS. And then again, if I want to use layer 3 to load balance the traffic across the uplinks, I can do that as well. So you start to get these, what are independent control planes that are running in a system to be able to operate just as they did before inside of Linux. But we've taken their data plane, copied it, put it beside them, and then we sort of a priori determine what pipeline we're going to use. And then in the runtime, we use this infra P4D application to be able to take all of the requests from the different clients and apply that to the single data plane. Thank you very much. And I'll leave the rest of the time for questions. Thank you.
All right, Dan, thank you very much for this presentation. I'm not sure if you're online today. Let's see. There you are. Welcome, Dan. I see there's probably some questions. I have a question of my own as well. Maybe I can start off with that. Was there any specific reason why you decided to still keep OVN in the picture? Because the only use case, at least what I understand from you, is that you would like to have the FDB, so the layer 2 forwarding for the learning part. Why not just use the bridge interface and get the FDBs from that? Because that part is already there.
Yeah, so in our design, we could have used either. And we chose OVS because of the history of P4 OVS. That's exactly where we were starting. So we wanted to use OVS. We could have used, we will likely eventually end up supporting both. But in terms of where the requests are of what interface people want to use and people are familiar with, OVS was an obvious choice.
Okay, so but you using it purely as a layer 2 switch, right? So if people start configuring like the ordinary, OpenFlow rules, that will no longer work. I guess it will mess up your configurations. Is that correct, or is there like a mixed way where they can still have the OpenFlow rules installed and use your hardware upload for maybe your routing or whatever part else you have?
Yeah. So what we've been doing is we're taking each individual feature, start layer 2. We'll start with routing, we'll start with ACLs, and start to move them over into the P4 pipeline. So the eventual goal is to replace the OpenFlow, so that, like the earlier presentation where we were matching ACLs to OpenFlow, we were doing similar things where we're taking ACLs to P4. So this is just part of the progression to try to make that transition. Yeah, if you wanted to preserve the OpenFlow in there, you could do that, but you wouldn't be putting those you wouldn't be putting your layer 2 into the P4 pipeline. You would just be keeping it in the control plane.
Okay.
So it's part of the it's part of the steps we're going to take to start to move more and more functionality into the pipeline.
Okay. Yeah. So basically that means that at that time you could obsolete OVS from the picture. I guess that's the ultimate goal.
They're definitely not the goal, but there are use cases where if you wanted your SDN controller to speak directly to that pipeline, it could do so. But there's a lot of things that OVS is doing that's beyond just simple layer 2 where it makes it super valuable. So I don't see that as the eventual end state.
Okay. Yeah, because I'm thinking about like, so if someone uses OVN in this scenario, right, that fully controls the OpenFlows to be installed. So if you combine the two, it will probably break your learning part, right, that you need for the layer 2 part. So you might end up adding additional layers inside OVN to get that running. Yeah,
so inside OVN is a separate topic, but we are, wherever there's an OpenFlow invocation, we're replacing it with a P4. And so it's part of that transition process, yeah.
Okay.
And that project still uses OVS for some of these virtual layer 2 functions.
Okay. Good. Thanks. I see there's no other questions, so I have one more question, and that is related to the implementation and the communication with OVS. I see you still have like this extra arrow that pushes you the FTP data through your what you call it, OVS runtime server. So my question is that for a specific reason? Because I think the normal path for us is, go from OVS vSwitchD to the OVS vSwitchD database, and then you can pull it from there, which also gives you updates. I don't think FTP is currently there, but that would have been a move to move that data to the database as well.
Oh, interesting. Yeah. So we want to start to engage back with the OVS community now that we have our patch and it seems to be working, to suggest, okay, what's the best way for us to be able to call this P4 runtime function in the cleanest way possible. I think our original set of P4 OVS patches were pretty intrusive. So our goal here is to have something that is really lightweight and doesn't impact or interfere with anything else. So yeah, we're definitely open to suggestions like that. Like that sounds very promising. If we could have an FTP in the database, then we could just pull it from there and be really straightforward.
Okay, cool. Yeah, I think that's some upstream discussion that probably needs to happen. So yeah, please bring it over there to the developers mailing list, and then the discussion can probably start there. Okay. If you send it there as an RFC, I think people can take a look and start discussing it. All right. There is one more question coming. I think it's from Aaron. Let's see.
He doesn't like your idea.
Oh yeah, it's about the same discussion. So I think we can. I think we can take that offline if you file the patches, and we can discuss that upstream. That will be great. All right. So if there's no more questions, then thank you a lot, Dan, for your talk, and then we'll discuss it upstream. And I think we now.